An air standard cycle consists of the following processes: isentropic compression, heat addition at constant volume, isentropic expansion back to the original volume, heat rejection at constant volume. Part A. Sketch the cycle on a PV diagram and calculate the efficiency of the cycle and peak pressure. Part B. The cycle is modified so that the heat is added at constant pressure. The compression ratio is adjusted to produce the same peak pressure as before. Sketch the new cycle on a PV diagram and calculate the new cycle efficiency. So this is actually quite a long question. There are two different cycles to analyze, but we can use some of the same analysis for both cycles. So first of all, sketch the PV diagram for the cycle. See if you can spot what engine cycle it corresponds to, and then we'll go through calculating the efficiency and the peak pressure for Part A. Okay, so the PV diagram for the cycle, for the first cycle, is as follows. Start off at state 1. We undergo isentropic compression, constant volume heat addition, isentropic expansion, constant volume heat rejection. 1, 2, 3, 4, we'll label it. And you may recognize this now as an Otto cycle, so like a petrol engine. And accordingly, because it's a piston engine, reciprocating piston engine, we're going to label this minimum volume as the clearance volume, VC, and this maximum volume as the clearance volume times the volumetric compression ratio. We'll call that RV. Okay. Now, this is an air standard cycle, so we can assume that it's an ideal gas. And we want to find the efficiency. So the efficiency, or the thermal efficiency, is going to be defined as what we get out, what we want, which is work, and what we have to put in to achieve it, which is heat. So that's the work on this leg from 1 to 2, we'll label that W12, plus the work on this return leg, W34, and the heat that we have to put in to achieve this is from 2 to 3, that heat. This is heat that's coming out of the cycle, that's the waste heat that allows us to form the process. Q23, so that's our efficiency. At the moment we don't know either of these quantities. If we want to know something about heat or work, then the first law is a good place to start. So the first law says that delta U is equal to heat into the cycle minus the work done by the cycle, or by any process. But here the process, or the full process, contribute to a thermodynamic cycle. And so the state, we start off at state 1, go around various other states, but we always return to state 1 again. And internal energy is a state variable, or state function. Therefore, the total change in internal energy for the cycle is 0. So we know that the total heat input for the cycle and the total work input or output for the cycle are equal. That's to say W12 plus W34 is equal to Q23 plus Q41. So we need to be careful about our sign conventions here. Q41 will actually be negative because it's heat rejection. W12 will be negative because we're putting work into the system to compress it. And using that, we can write that the efficiency is going to be Q23. So we replace these two works with these two heats. Okay, so in order to get the efficiency, we need to know the ratio of the heat in and the heat out. So we've already said we're assuming this is an ideal gas process. And in that case, we have two constant volume heat addition and heat rejection processes. And we can relate and also, because it's an ideal gas, CV is constant. It doesn't depend on anything, temperature or pressure. Therefore, the ratio of the heat in and the heat out can be related to the ratio of the temperature differences here and here. And so now we need to find what Q41 over Q23 is, and we can say that's T1 minus T4 over T3 minus T2. So T4 is the start of the process, and T1 is the end of the process. T2 is the start of the process, T3 is the end of this process. Right. So now we can answer the problem in terms of temperature. And working around the cycle, we have various isentropic processes. We only know the initial temperature and pressure, but we do know the compression ratio, the volumetric compression ratio. So we want a relationship between this volumetric compression ratio and the temperature changes during the isentropic processes. And because it's an ideal gas, we can write that Tv to the gamma minus 1 is a constant. Or RV, I called it, VC over VC, that's the compression ratio of the engine in volume. So gamma minus 1 is equal to the inverse temperature ratio, so T2 over T1. And because both isentropic processes have the same compression ratio, that's also equal to T3 over T4. Therefore, we can rearrange this, do some algebra on that, and say that therefore Q41 over Q23 is equal to T4 T1 over T4 minus 1 and so takes a bit of informed guesswork to come up with this rearrangement, but you can see that T4 over T3 is something we have. T2 over T3 is something we can get from rearranging this line of equations. And if we do that, and I'll leave it to you to do, minus 1 over RV to the gamma minus 1. And this tells us what our efficiency is. If we look back to here, efficiency is equal to 1 plus, in fact it's going to be minus, so we have a minus sign here. If we put the numbers in, we know that the value of RV is 5, and for air, gamma is 0.4, sorry, 1.4, it's in your data book. Value we get is 0.475 or 47.5%. Okay. So that tells us that the efficiency of this idealized Otto cycle only depends on the volumetric compression ratio. And in the idealized case, without mechanical losses, etc., we can be looking at 48%. So the next part of the question is to find the peak pressure in this cycle. So I'm just going to make some space on the board. And we need to think how we can achieve that. So we know something about the temperatures going around the cycle, but now we want to know something about the pressures going around the cycle. And what we can use either isentropic relations to get this, or we can apply since we already know the temperatures, having deduced them using isentropic relations, we can now use the ideal gas law. And what that tells us is that PV equals RT. And in particular so we can say that P3 is equal to RT3 over the volume at point 3, which is VC. If we consider a different point in the cycle, say point 1, we can say that, so hold on. In here we can come up with an expression for T3, because we've considered the isentropic processes around the cycle and the heat addition, but we don't know what VC is, or R over VC is. So what we can do is we can look for another point in the cycle where we know both pressure and temperature, i.e. point 1, and use that to deduce what the value of R over VC is. So we can write, so we can write P1 is equal to RT1 over RV/VC. This is a different volume. And from this we can extract the value of R over VC, which tells us that P3, and substituting into here, is equal to P1 over times RV over T1 times T3. So here we have this temperature ratio. And so we need to find out what T3 is, because we know what T1 and P1 are, and what RV is. So we can work around the cycle and actually put the numbers into the different temperatures. So let's find T2 is equal to, using the isentropic relationship, RV to the gamma minus 1 times T1. If we put the numbers in, that'll give us 548.2. Now we need to find T3. We're starting at T2, we're putting in heat, and we're told in the question how much heat per kilo. So it's going to start at T2, and then how do we convert this heat input of 2,000 kilojoules per kilogram into a temperature change? And in order to do that, we need to use the heat capacity. So we have 2 times 10 to the 6 joules per kilogram. If we divide that by the specific heat, for a constant volume process, this is CV. And for air, the value of CV, in fact, if you've just solved the previous question, you'll know this, is 720 joules per kilogram per Kelvin. And this will give us a value for T3 of 3026 Kelvin. So putting in the values to find P3, that's equal to P1, which is 1.01 bar, so times 10 to the minus 5, 10 to the 5 pascals. RV is 5. T3 over T1 is 3326 over T1 is 15 Celsius, or 288 Kelvin. And the value I get is 58.3 times 10 to the 5 pascals, or 58.3 bar. Okay, so part B. The cycle is modified so that the heat is added at constant pressure. The compression ratio is adjusted to produce the same peak pressure as before. Sketch the new cycle on a PV diagram and calculate the new cycle efficiency. Okay. So just to put the new PV diagram alongside the old one, take a moment to sketch it out yourself. And when you do so, it will look like this. So the same peak pressure, we're told that we adjust the cycle so it has the same peak pressure. So 0.3 is the same pressure. Sorry, this will no longer be 0.3. This is our peak pressure. We start off at the same condition. We compress right up to the pressure, have constant volume heat addition, isentropic expansion, constant volume heat rejection. 1, 2, 3, 4. Now, this is a typical model of a diesel cycle, or an air standard model of a diesel cycle, where we have, instead of constant volume heat addition, we inject the fuel and it burns at the maximum constant pressure. Okay, so let's label these volumes again. RV, VC. We have a new volume here, which we'll call alpha VC. Alpha is known in the industry as a cutoff ratio, and this is the clearance volume VC. Okay, so we need to go through a similar process to the previous cycle in order to calculate the efficiency. So write out the equation for a general expression for the thermal efficiency and think about how you can get it, and then we'll go through it. So the thermal efficiency is defined by the work we get out, and here we have work not just from the expansion and compression, the isentropic expansion and compression, we also have work associated with this constant pressure process. So we have work 1, 2, plus work 2, 3, plus work 3, 4, all over the heat that it costs us to achieve that, which is Q, 2, 3. Again, we're going to look at the first law to find the relationship between work and heat. So work 1, 2 plus work 2, 3 plus work 3, 4 is equal to Q 2, 3 plus Q 4, 1. And therefore we can rewrite the efficiency as so we're again working in terms of this heat rejection versus heat input ratio. And in the previous Otto cycle, this ratio was just the ratio of temperature differences. However, now, while we're still rejecting heat during a constant volume process, so that this heat output will be the mass times heat capacity, or constant volume heat capacity times temperature difference, this heat is added at constant pressure. So that means that we need to use a different heat capacity. We're going to use CV for the top one and CP for the bottom. And then the temperature ratio, temperature range is T1 minus T4, T3 minus T2. Now, we know this ratio, CV over CP, is gamma, or it's known as gamma, or 1 over gamma. So we now need to know what the temperatures are around the cycle. So we've been through this process to some extent before. We can think about individual processes. So let's talk about process 1 goes to 2. This is an isentropic compression. We know the volume ratio and we want to know the temperature change. And I'm just going to write this out without too much explanation to say that T2 is equal to T1 times the volumetric compression ratio power of gamma minus 1. That comes from the isentropic relationship between temperature and volume. 2 goes to 3. What's the temperature change across there? That's a constant pressure. So now the process 2 goes to 3. This is a constant pressure heat addition. And so what relationship can we use? We know that the pressure is the same. We know, or we can write in terms of the different volumes, what the different volumes are. And so we could use the ideal gas law, because then the only remaining unknown is the temperature. So we know that P2 is equal to P3, and from the ideal gas law, P equals RT over V. And so 2 over B2, which is VC, and that's equal to RT3 over the volume at 3, which is alpha VC. Rearranging that to find what T3 is, T3 is equal to T2 times alpha. That's it. And that's equal to alpha times the value of T2, which is RV to the gamma minus 1 times T1. So I've just substituted in the value for T1 there. Now the last process, or next process, state 3 goes to state 4. It's isentropic expansion, so we again apply this isentropic relationship. And we can write T4 is equal to T3 times alpha over RV. That's what the volume ratio is, gamma minus 1. And substituting in this value for T3, we find that T4 is equal to T1 times RV to the gamma minus 1 from here, times alpha, multiplied by this ratio, alpha over RV gamma minus 1. Now we can simplify this a little, and what we get is that T4 is equal to T1 times alpha to the gamma. So that's a bit of algebra for you to check. Now the last steps in order to get the efficiency, we just need to substitute these different temperatures back into our expression for efficiency, and we should get the answer. So make sure you can do this, but I'll just write the answer down here. Okay, so we now know what this temperature ratio is, and efficiency is 1, and if we reverse the order of that, it becomes not plus but minus alpha to the gamma minus 1. So I've just put a minus sign there. So that's our expression for efficiency. Now if we compare that with the efficiency of the Otto cycle, the Otto cycle had the same expression but without this term involving alpha. Or it would be, if you had alpha was 0, this would effectively be a constant. All the heat addition would occur right at one volume, so it would effectively be a constant volume heat addition cycle. So when alpha is non-zero, then non-unity. When alpha is greater than 1. So what does this mean? If we compare this with the efficiency of the Otto cycle, which was just 1 minus 1 over RV to the gamma minus 1, we have this additional term involving alpha, the cutoff ratio. What we find is that as alpha becomes greater than 1, so we have more and more heat addition, the efficiency gets reduced. So by burning at constant pressure rather than constant volume, we're losing some of the work. Now let's put the numbers in there, and when you do so, what you should find is that the efficiency, we don't yet know what the values of alpha and RV are. So, in order to find those, we need to think a bit about what some of the conditions that are specified in the question. The compression ratio is adjusted to produce the same peak pressure as before. So that tells us something about the volume ratio, RV, for this first compression process. So for this first compression process, we know the initial pressure, and because we know the final pressure is the same pressure we calculated for the Otto cycle, we know the pressure ratio for this process. And if we know since we know it's adiabatic, if we know the pressure ratio, we can deduce the volume ratio, RV. So P2, which is known from the Otto cycle, P1, which is our initial condition, is equal to RV to the gamma. Now P1 was 1.01 bar, P2 was 58.3 bar. We take a logarithm of both sides. Just put the values in, so P2 was 58. So that's the log of the pressure ratio. Then a bit of algebra tells us that RV is equal to the exponential e to the power of 1.4, which is gamma, log pressure ratio 58.3 over 1.01, 18.1. And that's fairly typical compression ratio for a diesel engine. And this is, as we mentioned, the diesel cycle. So we need to come up with a method to find the value of alpha for this constant pressure heat addition process. What do we know about this process? We know the amount of heat added from the question was 2 megajoules per kilogram. We know something also about the temperature at 2 and temperature at 3 because we calculated those in order to find the efficiency. So if we know the temperature change and we know the heat added, then we should be able to deduce to deduce the volume ratio. So the heat added is 2 times 10 to the 6 joules per kilogram, and that's equal to, since it's a constant pressure process, Cp T3 minus T2. And we can say, if we substitute in the expressions that we calculated earlier for T3 and T2, Cp is equal to alpha minus 1 times Rv to the gamma minus 1 times T1. So rearranging and putting the numbers in, alpha is equal to 1 plus heat input 2 megajoules per kilogram over the heat capacity Cp, and you should be able to remember this number if you use it often enough. It's in your data book. 1.005 joules per kilogram times 10 to the 3 joules per kilogram per Kelvin times 1 over and T1 was 288 Kelvin. So that gives a value of alpha of 3.169. And now we can put that straight into our value for efficiency, our expression for efficiency. And that's just to show you what the numbers are so you can check them. 1 minus, so I'm actually missing from somewhere okay, so I should have multiplied this or divided by gamma as well, because in the ratio of the heats there was the factor of gamma. And the value you get there is 0.584, 58.4%. So the diesel engine, although it's in principle not such an efficient engine because we're burning at constant pressure, because we're actually running with a significantly higher compression ratio, 18 versus 5, we're achieving a higher overall efficiency. But it really exercises your ability to apply the isentropic compression and expansion calculations, to apply the first law, and to use the ideal gas equation as appropriate.